All right, I got the thing tuned, a little bit involved. So I'm just gonna sort of recap what I did to get the tune good. Now I've sort of talked about how I've fixed the barrow and made some physical adjustments. One of the other things I did was really get a great calibration on the IMUs. So you can see on my little setup here, I've got my PCE byte, which is really for holding PCBs, but makes quite a nice whoop carrier, dead level. And so I did a good Excel calibration using that, and obviously set level and the other sides. And then I redid my temperature calibration really accurately from quite a low temperature up to 85. And the reason I wanted to do that was what I was finding was I was getting gyro errors when I was powering on the whoop. And I think what was happening was at power on, the thing was relatively hot, and so the but cool relative to the calibration that I had. So I kind of fixed that by doing a really great temperature calibration, but also calibrating the Excels with the battery connected, so it was sort of a little bit more representative. And that then meant that the IMU was stable across the whole temperature range. And there's quite an easy way of checking that, so I'll just show you that here. So what you need to do is set log disarmed to, okay, so I've got log disarmed set to 2, which means it's logging while disarmed, but not when it's connected to the USB. And then also do need to make sure that you've got IMU logging on. So I just got regular IMU, not raw IMU. And then if you do that, I just so I'm going to disconnect this and power it on with the USB disconnected. Now it is important that it's dead level while you're doing this. So I've got log disarmed on, so it will now be logging. And what I'm going to do is let the copter warm up with that logging on just in the stable state, and then I'll show you the log. So come back when the log is done. All right, so I've got the log, I've downloaded it. I used Mavproxy, you can use Mission Planner. And what I'm going to do is graph, we can't see with my face there, so I'm going to graph Excel Z, so this is the down component, and that should be force of gravity minus 9.8, and then I'm also going to graph the temperature of the IMU. So this is IMU, Excel Z and temperature, so you can see the temperature's going up nicely from 45 to 85, so this is why it's important to graph all the way up to 85. I mean, ideally I'd probably put it in the fridge as well. So when I'm doing the temperature calibration, put it in the fridge as well, so get right down to 18, but that's a nice sort of temperature graph. And then what we should be able to see is if we drill into this, you should basically see that this is 9.8, so it's 9.75, 9.75, but essentially, apart from a little bit up here, this is flat, and that's what you're looking for. And what you don't want is sort of a big wavy line here with the force of gravity varying, which you can see if you don't have a good temperature calibration. And what that means, if you don't have a good temperature calibration, what you'll find is when you fly the thing, it might start off level and then you get the leans, or it'll start going up or down, or all over the place. But to tune it, we need the thing to fly level, and so that requires the IMU to be well calibrated. So just put that so you can see that's worked out quite nicely. So I'm very happy with that. Now, the other thing, just sort of to round this out, so this is done using the temperature calibration, which I've got videos of before, but just a reminder, put it in the fridge, let it cool down to 5 degrees or whatever you want to have. INS TCal 1, enable set to 2, which is learn, and then you also need to set the Tmax, so I set that to 85. Now this isn't enabled by default on F405s, 1 megs, so I've created a custom build that includes this, and I'll post details in the video, because there's a bunch of other stuff that's needed as well. So that was the first step. Then I also mentioned I was using the fast rate. So this is, so the settings we've got here are fast rate, and I've set fast rate enabled to 2. So again, this will only work in either 4.7 or the custom build that I'm going to set up, which should be against 4.6. Regular 4.6 won't work because you won't have these features. This is a 4.7 feature. So set the fast rate enabled to 2, which means it's enabled, but it scales down when you're not armed. And then I've set the divider to 2, so that means divide the gyro rate by 2 to get the fast rate. And the gyro rate is INS gyro rate, and I've set that to 1, which is 2 kilohertz in this case. So gyro is running at 2 kilohertz. Fast rate is that divided by the divider, which is 2, so that gives you 1 kilohertz. And then the final piece is the schedule loop. So this is the main loop rate. I've set to 200 hertz. Default is 400, and that just gives me a bunch of headroom in terms of CPU load. So that's the fast rate. Now the other thing I did was I did a bunch of EKF configurations, so I want to really rely on my calibration, not on the learning of the EKF, which only works well if you've got lots of sensors, and I think I only have two sensors, IMU and the baro, so the chances of EKF learning very bad things is quite high. So if I connect with MAV proxy here, and what I can do is I can say param diff, so I can show you the difference between my parameters and default. And what we're interested in is these EK3 values. So I've set glitch radius to 0, EK3 glitch radius to 0. So this is always, my experience, is a good idea for small copters, because it basically means that when the sensors are very badly wrong, GPS in particular, the EKF will still keep assessing things rather than just giving up. That's a very poor explanation, but that's the way I understand it. Now, apparently this value affects the height estimate as well, even if you're not using the GPS. So that's why setting it to 0 is a good idea. So then I've divided the altitude noise gate by 10. This is, I just find, let's find some find some docs. Okay, so actually I can just do it in this guy. So if I go to EK3 alt M noise, right, so you can see here there's an RMS value of noise in the altitude measurement. Increasing it reduces the weighting of the barrow measurement, make the spin filter respond more slowly to barrow measurement errors, more sensitive to GPS and accelerometer errors. So I've basically weighted this towards the barrow by dividing it by 10. So I said barrow's the only thing I trust for height, so please use it. So that's my first setting. Okay, my next setting is the height eye gate. So this is, now I've set this to 300 from 500. That's basically based on the docs for glitch radius, EK3 glitch radius, that says you should do this. So I've just copied that. And then these are the two important ones. So G bias P noise, A bias P noise. So this is the rate at which the EKF learns gyro and XL biases. And you can see that I've divided both of those by 10. And that means that the EKF learns much more slowly biases. So I ideally don't want to switch it off because I want some bias estimation learning to go on, but I don't want this to be a high rate of learning, because it'll basically learn offsets from noise from the accelerometers, which is bad. So I divided these by 10 as well. So those are my sort of EK3 things, and then you can see the EK3 source, I set a bunch of things to 0 because I don't have GPS or compass. And then the final thing was this ground EK3 ground effect DZ. So this is a height in meters, and what you're supposed to do is look at the ground effect offset of the height of the barrow and set this value to half a meter less than that value. So in my case, I was getting this 2.5 meter dip in the log, and so 3 meter dip in the log, and so I set this to 2.5. So those are my EK3 parameters. Now, if I then look at just the barrow situation, so here is a log from me holding the copter in my hand and raising the throttle, and so you can see the throttle out, which is this green line going up. So I'm raising the throttle from 0 to like 75% throttle, and then I'm comparing that with the pressure, and you can see that the pressure goes down due to this vacuum effect, and it goes down pretty linearly. And so I then sort of figured out what the difference in pressure I needed was to get that to be flat. And in my custom firmware, that is going to be Pavo20 thrust scale. Sorry, so this is that's the value. It's not set for this log. So now we'll have a look at a log. Sorry, so I did set it, and the value I came up with was 130, I believe. I think if I go to the log we've just taken, oh, I don't have that. Okay, but yeah, so I set this to 130. And then the final thing is to show you what this barrow error looks like when it's bad. So I'm graphing, so this is just me trying to fly, so graphing throttle, so this is where the thing takes off, and I'm graphing this value XKF4SH, that's down here, So this is the square root of the height variance, and this basically should stay under 1 at all times, and you can see it's nowhere near under 1. It's shooting up to like 7.5, which means the EKF is very, very upset with the height variance, and this is why altitude hold did not work well at all. But if I look at a log, where I've got this compensation set, so we can have a look at what the parameter is set to. So I got Pavo 1. Again, this will only be in the custom firmware I'm putting together because it's a new feature. So I've got this Pavo 1 thrust scale minus 130, so that's in pascals. So basically it says offset the barrow by this much as a proportion of throttle. So if you're at throttle, full throttle, you'd get an offset of 130, and then it'll be done over that range. So if I look at the barrow output, you'll see that the pressure is being compensated. So I've got this compensated pressure. So this is the absolute pressure, and this is the compensated pressure, is this green line. So you need some pressure difference because obviously taking off. And if I look at the altitude looks very believable. So 1.5 meters is probably roughly right. And you can see this is where I get this ground effect dead zone 4 from. So I said, okay, so this is, so when you take off, you raise the throttle and you get this ground effect that basically causes the pressure to rise because of the prop wash against the floor, against the ground, which means it looks like the altitude is going down. And so this is this maximum value of about 3, and you've got to subtract half to get the rough outline of that thing. So you can see here, good set of data. And if we look at this magic XKF4 here, you can see now that there's still some variance at the beginning, but for most of the flight it's much more down under 1. Still not brilliant, but pretty good given this copter. So pretty pleased with that setup. All right, so I'll probably, that's sort of okay, so that's probably the sort of setup video. I'll probably switch to another video just to talk about the auto tune, because that deserves a little bit of a video in itself. Thanks for watching.